In this video, we're going to discuss risk, relative risk, odds ratios, survival analysis, logistic regression. And as our example data set, we're going to use a study I participated in a few years ago. It's kind of fun. It compares a personalized parent voice smoke alarm with a conventional residential smoke alarm. And what would happen is that the kid would children would come into the sleep lab, and their mom would record an alarm message. So, for example, Johnny, wake up, get out of bed, leave the room. And the alternative was a tone alarm at 100 decibels. Now, 100 decibels are on a log scale, and most typical smoke alarms in a house are at 80 decibels. So this was a very, very loud signal, and it was left on up until the child left the room or 5 minutes had passed. So the child was instructed as to what to do. They were wired up to an EEG machine, and when they had been in stage 4 deep sleep for 5 minutes, the alarm went off. Now, this was actually a crossover trial. The kid went to sleep twice and got blasted. But we're going to treat the data set in just a simple manner and pretend like they were all independent events, but you'll still get the basic idea. So here's our data set. Oops. Here is our data set. So we have 3 variables. They got out, yes or no, the number of seconds it took, and whether they were in the control, which was the tone, or the parent's voice. So what we would normally do is a little crosstab. If we're not looking at seconds, we'll look at seconds later. But we're going to have the groups be the group, the mother or the tone, and the columns is got out, yes or no. Our statistics, we're going to look at chi-square in order to determine if we can reject the null hypothesis. And just a reminder, the p-value from the chi-square is the probability of finding a chi-square value as large as we get or larger, given that the null hypothesis is true. And then we're going to choose a risk box. This tends to be a little tricky because the direction and everything of the risk kind of depends on how you've labeled everything. So we have got out, no is a 0, and yes is a 1. Our groups, the control is 0, and the parent voice is 1. Okay, let's see what we get. So we have a little table here. There were 24 controls, 24 parent voices. Again, this is not how you would actually do this analysis, but for now we're going to do it this way, have data laid out in this format. It'll get the idea. We're treating it as though it was a between subjects design, but actually there were 24 kids and they got each condition. So of the tone, there were 24 attempts. 16 of the children did not leave the room. 5 minutes of 100 decibels, and they slept through it. Well, they didn't all sleep through it, but they didn't get up and leave. And some of them got up and left and never actually woke up. It was kind of interesting. Anyway, 9 children did, or 8 children did manage to escape. When they heard their mom's voice, only 5 stayed asleep. 19 successfully escaped. So the question is, are these numbers randomly distributed given these marginal totals, and the chi-square value of 10 says definitely not random. So we reject the null hypothesis. Now let's look at the risk estimate. Now this is the odds ratio for the group for the variable with control and parent voice. Now, one of the things when you set up your rows and columns, you have to be careful. You want to make your rows the treatment effect and the columns the other. So you have to think, is this a reasonable number, and in which way is this reasonable? And so since that's such a high number and this is such a high number relative to that, you're going to say the odds ratio is the risk of not escaping given that you're in the control group. Let's see how we would calculate this by hand. So to calculate an odds ratio, we can't calculate, or we're not going to calculate relative risk in this environment. We're just going to look at the odds ratio. And what we do is we're going to, in a relative risk, we calculate the probability going this way, 16 out of 24, and divided by 5 out of 24. In an odds ratio, we don't have the prevalence, so we're not going to go across this boundary. So we're going to look at 16 divided by, now we don't divide by 21, we divide by the parent voice. Now again, this is we're going in this direction, and we're going to look at 8 divided by 19, and then we're going to take this, this is the odds. These are odds, 16 over 5, 16 out of, or 16 one way, 16 to 5, and 8 to 19. We're going to take that divided by these odds to get the odds ratio, and it's 7.6. Now what does that mean? That means that if you are in the control group, your risk is 7.6 times of not escaping. Your risk of escaping in the control group is 7.6 times your risk being in the parent voice group. And if we take the inverse of that, that's the protective odds ratio. So your risk is a lot less if you have parent voice. Okay. Now, let's figure out what the relative risk is. Now remember, an odds ratio is an estimate of the relative risk. But what we want to know is, we don't have prevalence, so let's figure out what our prevalence is. Now we could do 21 out of 48, but that has the parent voice. Really the prevalence is if you just have a regular fire alarm, and this is more intense than a regular fire alarm. What is the probability that you don't escape? And that's going to be equals 16 out of 24. So that's the prevalence we're going to use here. We don't really have an estimate of prevalence, but we're going to use that. And to calculate it, we use this formula OR divided by 1 minus prevalence plus prevalence times OR. And what is that? That equals the odds ratio, 7.6, divided by 1 minus the prevalence plus prevalence times the odds ratio. So this gives us 1.41. Now notice our estimate of the relative risk is a little bit less than our relative risk given this prevalence is a little less than our estimate here. So the odds ratio is always an overestimate. In this case, it's a pretty big overestimate because our prevalence is so high. They are pretty close to the same thing, the evidence, the odds ratio and the risk ratio, when the prevalence is less than 10%. Here it's way over, and so the odds ratio is way over. So you have about a 41% chance, greater chance of burning up if you have a regular fire alarm as opposed to your parent calling you to wake you up. Of course, I imagine in a real-life situation, your parent would come and drag you out whether you woke up or not. But still, that's the ratio here. Now, another thing I wanted to look at was survival curve. So how long does it take to get out? And to do that, we're going to go analyze and do survival. And there's different ones. Life tables, that gives you tables of survival. The Kaplan-Meier is actually a way to compare two groups and draw a curve, a Kaplan-Meier curve that graphically illustrates. Cox regression is if you have continuous variables. We have, in this case, our predictor is group, tone, or voice. And Cox with time-dependent covariance refers to if the covariate changes over time. We're going to do a Kaplan-Meier curve, keep it simple. And in this, we have seconds. So let me reset this. We have seconds. That's the time to get out is seconds. The status is they got out or not. The event is we enter a 1 if they successfully got out. And the factor is the group, parent voice or tone. And we want to compare factors, and we're going to use a log rank test. That's probably the most common test used, and that's testing basically whether the curves are similar, the same. And then under options, come here. Okay, I'm not going to get it over there. So options, our statistics, we're going to want to ask for oh, this is interesting. We seem to be locked up here. Okay, let's see what happens when we run it. Okay, we get a survival table. I'm going to do this again because for some reason it locked up. Let's see if we can not have it lock up. Here we go. So I uncheck the survival box, I check the mean and median survival, and I want a survival curve. I'm going to do a 1 minus survival because that's what was in the paper. Okay, we'll hit continue. Okay, and we get these two curves, which are mirror images of each other. This is the cumulative survival. This is 1 minus survival. Now, what do we mean by survival? We don't mean that the kid burned up, but rather we mean it's time to an event. In survival functions, it comes from studies mostly centered around death. But in this case, it's time it takes for the kid to run out of the room. And at the beginning, everybody's sleeping. They're in a nice stage 4 sleep. They've been sleeping for 5 minutes and they feel pretty good. And then they're blasted, either with mom's voice, which is the red line, or the control tone, which is the blue line. And as kids leave the room, the probability that they're going to leave the room gets lower. So at the end of the 5 minutes, 20% of the kids were still in bed, whereas about 70 or 65 to 70% of the kids were going to fry after 5 minutes, at least 5 minutes of warning. So this survival function, this Kaplan-Meier curve, which is adjusted as kids drop out, meaning they escape, then the calculation is based on the remaining kids. And the confidence intervals get broader as you go out, pretty tight at the beginning, and then they get wider as you go, as the n decreases. This is very descriptive. I mean, the curve is different everywhere from the beginning to the end. It's a steeper slope, it starts sooner. It's just very descriptive of the issue. This graph is the same way. This is time it takes to escape. This is time you're still sleeping or in bed. Time to escape. Mirror images of each other. So this is a pretty useful type of analysis. I want to show you one more thing. Let's go to Regression Logistic. Now, I didn't save extra variables, for example, like age or something that we can control for. I just want to show you straight out whether or not the kid got out, and as a function of group. So got out, yes or no, that's a binary variable. That's where logistic regression is appropriate, when the outcome variable, the y equals a plus bx, the y is binary. And we'll just, really, there's not much else to do. You don't really need categorical when there are only 2 groups. If there were 3 groups, you'd want to click on that. Options, you don't really need anything from here. We're not going to save anything, so let's just run. All right. So here's where we reproduce our table from before. We see up here we have, in the original crosstab, 16.8.5.19, 16.8.5.19. It shifted around a little bit. This is predicted, this is observed, predicted by the model, and these are the variables in the equation. So we have a constant, and we have a coefficient 2. Now, the logit is the natural log of p over 1 minus p. And when we get this, when we make this a linear y equals a plus bx, to convert this coefficient, we can convert it into an odds ratio. And the odds ratio is 7.6. Whoa, it's the same as we got over here. 7.6. So we get the same answer and our prevalence. One thing, let's just check here for 1 second. So the constant, when you have just this situation, the constant actually represents the, can represent the prevalence, which is 0.5 because our subjects were equally running in control or parent voice. So if we were to plug into our equation, rather than 0.66, if we use 0.5, we would get a 1.8 relative risk. Still not anywhere near the 7.6. So those are some things to consider when you're doing an odds ratio. I suppose, well, we can't really talk about anything else with this. So that's it. Thank you. I am trying to, you can turn your video off as soon as I can figure out how to get my little thing there. It is.